Welcome to this explainer. I'm absolutely thrilled you're here today because we're about to take a really dynamic journey into the invisible, microscopic rules that literally build the world around us. Have you ever wondered why some materials are rock solid while others just burst into flames the second they touch water? Or, why two incredibly dangerous substances can suddenly combine to create something you eat every single day? Well, the answer lies in the atomic world. And today, we're going to completely demystify it by mastering the secrets of ionic bonding. All right, let's dive right in with a pretty shocking example. What you're seeing is raw sodium metal being handled with tweezers, and it's kept completely submerged in a jar of oil. Why oil? Well, because sodium is so violently reactive that if you just left it out in the open air, or worse, dropped it into water, it would vigorously react and literally explode. It is incredibly unstable on its own. But now, consider this: a totally normal, everyday salt shaker. The table salt inside this shaker, which, let's be honest, you probably sprinkled on your fries just this week, is actually made of exactly that same explosive sodium combined with a toxic green gas called chlorine. Yet, in this form, it's completely safe. You can hold it, you can eat it, it's totally 100% stable. And this just brilliantly illustrates nature's ingenious solution to atomic instability. I mean, how do we go from a dangerous, explosive element to a delicious, perfectly stable compound? Well, this drastic change in behavior all comes down to the chemical bonds formed between the atoms. When elements combine to form compounds, their properties can completely transform. So how does this atomic magic actually happen? So here's our quick roadmap for today's explainer, specially structured to help you absolutely crush these concepts for your O-level exams. 1. The ultimate atomic goal. 2. The great electron transfer. 3. Bonding in sodium chloride. 4. Bonding in magnesium oxide. 5. The giant crystal lattice. And finally, 6. Properties of ionic compounds. Section 1. The ultimate atomic goal, or why atoms interact in the first place. To really understand chemical bonding, we first have to understand the hidden, invisible rules of the universe that drive all chemical behavior. Why do atoms even bother interacting with each other at all? Well, it all comes down to something called valence electrons. These are the electrons present in the outermost electron shell of an atom. You can kind of think of valence electrons as the essential currency of the atomic world. These are the only electrons that atoms use to trade, share, or give away in order to buy themselves chemical stability. And what exactly are they trying to buy with that currency? They're trying to fulfill the octet rule. You see, most atoms are basically envious of the noble gases on the periodic table, elements like neon and argon. Noble gases are completely unreactive, cool, and stable because they already have a perfectly full outer shell of exactly 8 electrons. For all the other atoms out there, their ultimate goal in life is to achieve that fully filled, stable outer shell. And they will chemically react and combine with almost anything to make it happen. Moving on to Section 2, the great electron transfer, how atoms go about solving this atomic instability. Notice the clear division of labor here between metals and nonmetals. Metals, like sodium or magnesium, typically have just 1 or 2 valence electrons. So it's just much easier for them to ditch those extra electrons to empty their current outer shell, revealing a perfectly full shell underneath. When they lose these negative electrons, they become positively charged ions, which we call cations. On the flip side, nonmetals, like chlorine or oxygen, have mostly full outer shells. They're usually just 1 or 2 electrons short, so they eagerly scoop up those discarded electrons to finish out their set. Gaining negative electrons turns them into negatively charged ions, known as anions. Definitely lock these 2 exam terms into your memory right now. Cations are positive, anions are negative. Section 3. Bonding in sodium chloride, forming an actual ionic bond. Now that we have our players, the metals that want to lose electrons and the nonmetals that want to gain them, let's simulate a dynamic 3D zoom right into a single microscopic interaction. Let's walk through this incredible hero's journey of an electron. Step 1. Our sodium atom has an electron configuration of 2, 8, 1. It desperately wants to get rid of that one lonely outer electron. Step 2. A chlorine atom floats by. Its configuration is 2, 8, 7. It is starving for exactly 1 electron to reach that perfect 8. It's basically a match made in heaven. Sodium transfers its electrons straight to chlorine. Now for step 3. Because sodium lost a negative charge, it becomes a positive Na plus cation. And because chlorine gained a negative charge, it becomes a negative Cl minus anion. And what do opposites do? They attract. This incredibly powerful mutual electrostatic attraction between the positive and negative ion is exactly what we call an ionic bond. All right, section 4, bonding in magnesium oxide. What happens when we're trading multiple electrons? So that first example was a simple one-to-one trade. But what happens when atoms need to trade more than just a single electron? The absolutely crucial point here is looking at the valency. Magnesium has an electron configuration of 2, 8, 2. So to reach stability, it needs to lose exactly 2 electrons. Oxygen, on the other hand, has a configuration of 2, 6. To get to 8, it needs to gain exactly 2 electrons. Once again, nature provides a perfect fit. Magnesium transfers both of its outer electrons directly to oxygen. Notice the result here. This creates a highly charged magnesium ion with a +2 charge and an oxide ion with a -2 charge. Because the charges are equal and opposite, they bond together in a 1-to-1 ratio to form the compound MgO. Section 5, the giant crystal lattice. Time for zooming out. We've been looking at just single pairs of ions so far, right? But to truly understand the world around us, we really need to zoom back out. When you hold a single grain of salt, you aren't just holding one sodium ion and one chloride ion. You're actually holding billions of them. And we know exactly how they're arranged thanks to an incredible scientific technique, X-ray diffraction. By firing X-rays at salt crystals, scientists capture these stunning diffraction patterns, which prove that these invisible ions don't just clump together randomly. Not at all. They stack up in a highly organized, giant, repeating three-dimensional structure. We call this structure a giant ionic crystal lattice. Inside this solid structure, positive and negative ions alternate perfectly. In sodium chloride, every single positive sodium ion is tightly surrounded by 6 negative chloride ions, and every chloride is surrounded by 6 sodiums. This creates a deeply interconnected network held together in all directions by exceptionally strong electrostatic attraction. They are literally locked into a rigid, highly stable grid. Which brings us to section 6, properties of ionic compounds. Let's look at the physical properties. So why does any of this matter to us? Well, because the microscopic atomic structure we just built directly determines the macroscopic physical properties we can actually observe, touch, and test in the science lab. Because those electrostatic forces inside the giant lattice are so incredibly strong, it takes massive amounts of heat energy to break them apart. That's exactly why ionic compounds like table salts have very high melting and boiling points, and why they're solid at room temperature. Seriously, you could put a pan of salt on your kitchen stove, turn it to max, and it absolutely will not melt. Furthermore, this tight lattice makes ionic compounds very hard. However, they're also quite brittle. If you hit a salt crystal with a hammer, you shift the aligned layers of ions. Suddenly, positive ions are pushed right next to other positive ions, and they violently repel each other, shattering the crystal instantly. Now here is an absolutely crucial must-know point for your exams regarding electrical conductivity. Can ionic compounds conduct electricity? Well, it actually depends entirely on their state. In a solid state, the ions are locked rigidly in place inside that crystal lattice. Because they can't move around, solid salt is an insulator. It conducts nothing. But if you melt the salt into a liquid or dissolve it in water to make an aqueous solution, the lattice breaks apart. Suddenly, those charged ions are freed up. They become mobile charge carriers that can flow from one place to another, meaning molten or dissolved ionic compounds instantly conduct electricity. It's a real game changer. So, we've successfully unraveled the mystery of the ionic bond. We've seen how metals generously give away their electrons to nonmetals to create a beautifully balanced, stable lattice. But before we wrap up this explainer, I want to leave you with a tantalizing puzzle to think about. We know nonmetals desperately want to gain electrons to fill their outer shells. So, what happens if you put 2 nonmetals in a room together? If neither of them is willing to give up an electron, how on earth do they bond? Well, you'll just have to join me in our next explainer on covalent bonding to find out exactly how they solve that atomic standoff. Until next time, keep questioning and keep learning.